Let's talk about lasers. I'm not going into detail how scientifically a laser works. There are much better videos out there you may watch first, but I want to show you some lasers that you may not have seen before. Let's start off with the one you may have seen before. That's a laser distance sensor. It has a small diode laser, about 1 milliwatt, and yeah, it's in almost every toy. It's boring, you can't burn stuff with it, you can't burn yourself, so let's turn it off and throw it in the fuck it bucket. People started to extract diodes from DVD burners back then, and then from Blu-ray burners. That's a diode from a Blu-ray burner. It's about half a watt to 1 watt at 4 or 5 nanometers. It's enough to engrave stuff and burn wood, even cut some wood. And in this case, it's literally just a diode in a housing without a driver. Diodes need special drivers because they can't handle reverse currents at all. And I mean, really microamperes, and it's dead. They're extremely sensitive to this. But this diode is also quite boring. I mean, it's enough to make you blind in an instant, but it's, well, there are much better options out there. So let's also throw it away. This is a 135 watt laser diode. Normally there's a housing on top with some mirrors inside that couple into a fiber. That's a 976 nanometer laser, which is used for pumping fiber lasers. Usually multiple of them in a cabinet. And I've seen this model or models from this brand going up to 350 watts. Nowadays you can get like 500 watt laser diodes off AliExpress for really cheap, but this is what we had a few years back. This diode is already powerful enough to burn almost anything, including you. But we can go even better. Let's sidetrack for a moment and look at some special lasers. If you want to see more laser stuff, you might check out the other channel, Xenodiladon. He's a cool guy working on show lasers and built himself a compact OPSL. Let's take a closer look what I have here. These are both OPSL lasers, optically pumped solid-state lasers that use a solid-state crystal to change the wavelength. Both have a pump diode, usually at 808 nanometers or 976, that gets reflected onto an OPSL crystal or silicon piece, which you can see here. That's the black dot. And over here, it's hard to see, also a small black dot. The pump wavelength of these diodes get absorbed by the atoms of the dopant in this crystal, and they emit their own laser light at a different wavelength. The different wavelengths then travels through a bunch of mirrors and lenses and even some second harmonic generators to create different wavelengths. In this case, both lasers were around 440 to 460 nanometers in wavelength, so I'm not quite sure how it does that exactly. This one was a coherent sapphire, which I've taken out of its housing because the cooling peltier on the bottom has cracked. And this one is from a coherent obis. It's almost the same, just way smaller. And also here the peltier has cracked due to physical damage, due to an impact. They're used in scientific applications, mainly research. They don't have a lot of power, even if the pump diodes have a lot after second harmonic or third harmonic generation. You lose a lot of power. So they're really just useful for their excellent beam quality and frequency stability, not for their power. Let's step it up a little bit. The first ever laser that was invented was basically a ruby rod inside a flash lamp, which gets pumped by the intense light coming from the flash lamp, and then it emits its own laser light at a specific wavelength that's bounced between two mirrors, whereas one is partially transparent. This creates insane amount of energy pulses coming out of it, but there is a way to even increase that by using Q switching. There are two types, passive and active Q switching. A passive Q switch is like a mirror that becomes transparent when a certain amount of energy is reached. And a passive one is, well, electronically controlled. The most common types of active Q switches are acousto-optical modulators and Pockels cells. I don't have the Pockels cells here, so I'm going to focus on this acousto-optical modulator. So let's take the lid off and see what's inside. It's some sort of crystal or glass type material with a piezo element attached to it. On the other side, you connect a RF driver at a certain frequency, which makes this crystal oscillate or vibrate physically. It creates a standing wave inside the crystal, which allows the light to be either passing straight through or get a little bit deflected to a second mirror. So you can non-mechanically switch your light from your pump cavity to the outside world. You can build up a lot of energy and then release it all at once. A Pockels cell works on a slightly different principle, but it does the same. It uses electricity to alter the polarization to do basically the same thing, but they're a little bit faster and can handle a little more power. Now let's take a look at the driver for this. So here we have the driver. The AOM crystal gets connected over on this RF port, and we have some control pins for controlling the amount of power going to the crystal. You can use the crystal to manipulate the light going through in very precise ways, like dimming it and creating certain type of pulses. So let's take off the lid and see what's inside. Here we have an AOM driver. As you can see on the left side we have an oscillator that generates, in this case, 40.68 megahertz, which then gets filtered and amplified by this power amplifier and also switched by the control electronics. And here we have a transmission line that's capacitively coupled to a second one for providing feedback, so we have a constant amount of power. It then goes straight out to the crystal. So now that we have an AOM, what do we do with it? Well, you need a few components for a working laser. You need the crystal that stores the energy. This is a neodymium YAG crystal inside a copper block, which gets thermally stabilized as they only work in a very narrow temperature range. It gets placed right next to the AOM. Then we have a collimator for collimating a fiber into a beam. The fiber is coming from the pump laser, in this case a 976 nanometer or 808 nanometer pump laser, depending on the crystal. I think for neodymium YAG it's 808, and for ytterbium YAG it's 976. So just imagine we have our extremely strong pump laser going into the fiber, getting collimated into the crystal and through the AOM. But that's not all. We need a mirror. It may not look like a mirror. It's a little bit reflective. It looks like a piece of glass, but it's coated with a special material that only reflects the light generated by this crystal, not the pump diode. So let's put that in front of it. Usually they are placed on a very flat bench, an optical bench, and are carefully aligned because any misalignment just makes it not work at all. In the end, we have another mirror. It's slightly parabolic and on a kinetic mount. So after bolting it down, you can tweak it ever so slightly to perfectly align the light path. And basically that's it for a diode pumped laser. You pump in the energy, gets bounced around inside the cavity, and when the AOM decides to switch over, it slightly bends the light so it doesn't get bounced around anymore and exits the output mirror. What we have then is a very short pulse with a lot of energy. Enough energy to vaporize metal. These types of lasers are also used in marking metals and other material processing applications, because the wavelengths that generated 1064 nanometers by the crystal is pretty useless for organic stuff. You can't mark wood with it, you can't burn yourself. It basically, your body is almost transparent to it, not quite. It scatters the light inside your tissue so much that, well, doesn't do anything. It may tickle a little bit, but you basically can hold your hand inside a fiber laser that's able to cut half a millimeter of steel, and, well, you don't get hurt. So let's fast forward a little. In the beginning, we had optics and lenses, but at some point, fibers started to appear. Using fibers made everything smaller and more powerful. And what I have here is a ytterbium fiber laser. It's one of the most common types used in those fiber laser engravers that's used for making custom metal engravings on, let's say, a phone's backside. A fiber laser is able to produce pulses in the order of like 50 to 100 kilowatts by just being pumped by a 20-watt laser. The pulses are very short and don't appear so frequently, so the average power is only 20 watts, but each pulse is so short and so powerful that it's able to vaporize metal. So let's take off the lid and see what's inside. And of course I opened the wrong end. This laser seems to be of MOPA type, which means Master Oscillator Power Amplifier. You have two circuits basically, one at a low power that's very precisely controlled, so you can shape your pulse, its duration and everything, and then send it into the power amplifier and it gets amplified. So let's crack open the lid and see what's inside. So here we go. Here we have the power amplifier part. It gets pumped by these two laser diodes, which I don't know how much power they have. I suspect around 20 to 30 watts each. They are connected in series. These lasers are at 976 nanometers. That's the wavelength that gets absorbed by the ytterbium atoms inside the doped fiber. Here we have these metal rods, which are Bragg gratings. Let's think about for a second, how do we create a cavity in a fiber laser? We can't have any mirrors because we would need to terminate the fiber at every mirror and feed it back in, and that would be a huge hassle and it would increase the cost quite a bit. So engineers came up with a way, which they called fiber Bragg gratings, that are carefully crafted fibers with different densities inside to only reflect the wavelength that the active fiber produces, in this case 1064 nanometers. The 976 pump wavelength gets straight through. And these are most likely the fiber Bragg gratings. Inside here we have the active fiber. I don't want to take this apart any further because I might break something, like this fiber here. Looks all right. Those glass fibers are very thin and very fragile. What you see here is not really the fiber. It's the plastic coating of it. The fiber itself is about 100 micrometers for the larger ones and even down to 6 micrometers for single mode fibers. I suspect this is one of the larger ones. It's easier to work with and can handle a lot more power. So let's take off the bottom cover. In case you wonder why I'm poking in here, the laser has a master oscillator failure. I don't know how to fix it, so it's basically strapped to me. Here we have the master oscillator. These are the same components as in the older laser. We have a pump diode, a seeding diode, probably two pump diodes, I'm not quite sure, and an acousto-optical modulator. with the RF driver. These are just for driving the laser diodes. We have 2 MOSFETs for driving these 2 and 1 for driving the power diodes on the bottom with its associated power supply. Over here we have 2 photodiodes that detect the pulse shape and length and controls everything through an FPGA and other electronics to what we want. These 2 diodes are about 1 to 3 watts, but if you look at the label it could be also 10 watts. I'm not quite sure. You can't find any data sheets on these. These go into the master oscillator, creating the pulse we need, and once we're ready to fire the pulse out, we send it through the AOM, acousto-optomodulator, and the pulse that's coming out of the master oscillator is already at 1064 nanometers. So it passes barely through the fiber Bragg grating into the power amplifier and kicks off all the energy stored in this fiber at the same pulse, shape and duration. So basically think of this like a hi-fi setup, where the master oscillator is your source, a very good DAC and preamp or record player, and the power amplifier as well, the power amplifier. You create a precise signal on your source and preamp and send it to the power amplifier, which then only amplifies it. This way we can get pulses of a length of about 100 nanoseconds with an average power in this case of 20 watts, and well, the pulse peak power is in the order of 5 to 10 to 15 kilowatts. I haven't calculated it, but there are calculators on the web where you can enter these details and it shows you how much power you get. You may ask yourself, what's this thing? Why does the business end have to be so huge? Well, you don't hear that often, right? This is a Faraday isolator. It prevents back reflections. Just think about it. You have a master oscillator that fires a 1064 nanometer pulse into your power amplifier in one direction. It comes out here, and when it reflects back without the isolator, it goes back into the power amplifier, gets amplified again, and potentially causes havoc. It destroys everything in here. The power that could get generated when firing back into the system could be like 5 times higher than the actual working power. So it could destroy diodes, photodiodes, even make fiber terminations that are not perfect just explode. These work by magnetism. I've cracked one open. So that's the 3 parts of this isolator. We have a polarizing filter. We have a strong magnetic field and a slug in the middle, and we have a polarizing filter at the end. The slug inside the magnetic field is actually a magneto-optical crystal. It twists the polarization of light in the same way, no matter what direction the light travels through. We can use that effect to polarize the light that's coming back and reflect it into a beam dump. So, for example, we send the high energy pulse through, polarize it in a certain way, and when it comes back, it gets polarized again and gets reflected by this polarizing cube into a spot where it doesn't damage anything. So, quite an interesting technique, and it's really necessary for high-powered fiber lasers. This is another type of fiber laser. It's a erbium doped instead of ytterbium, which allows it to have a wavelength of 1550 nanometers. This wavelength has different effects, especially on skin, whereas 1064 nanometers gets scattered into your skin and basically dissipates the energy over a large area. 1550 gets absorbed by the water in your skin and heats it up. These lasers are used for stretching your skin by creating microscopic burns that contracts your skin. So let's crack it open and see what's inside. 1550 nanometers is also a little bit more eye safe, a word you don't hear with high-powered lasers this often. It's far enough outside the visible spectrum that the transparent part in your eye absorbs this light, not your retina. 1064 nanometers passes straight through and burns your retina, and your retina is like a very sensitive image sensor that gets destroyed in no time. The glass part is a little bit more tough and it can withstand a little bit more power, but still, if you work with any of these, get yourself proper safety glasses that's rated for the correct wavelength and as much attenuation as possible. And I mean from a reputable brand like Thorlabs, Laser World, etc. Not some Chinese stuff. And remember, if the glasses have the same color that the laser what you want to block, it's totally the wrong type. Throw them away immediately. So let's take off the lid. Here we have, like in the ytterbium fiber lasers, the control board with the interface and all of that, the diode power drivers and the active fiber. I think the pump wavelengths of both lasers are about the same, 976 to 980 nanometers, which gets absorbed by the erbium atoms, and then a seed laser creates an initial pulse that gets amplified and sent out the business end. This laser apparently has 120 millijoules of power. That's a lot. And how it does that? Well, from a little bit of research, I found out that a meter of erbium-doped fiber can hold up to 40 microjoules for a really big fiber. That would mean in here there's several kilometers of fiber, which is not the case. It's barely big enough for it. Another method is to use several power amplifier stages. Each stage amplifies the signal by a certain amount. This way you need much less fiber. In this case, we still have a lot of fiber in here. If you look here, there's a bundle of a lot of erbium-doped fiber. And unfortunately I can flip it open. It usually flips open like that because this part is connected to the lower part and I will have to disconnect all the fiber stuff. And since I don't know how to splice them and weld them together, I rather leave it. This unit should still work, as you may have seen in this teardown video where this laser came from. The pulse power and average power of a laser is determined by the pulse length and repetition frequency. In this case, if we have really 120 millijoules of energy here, and as far as I know, the pump diode is about 20 watts, well, we can only fire it at 160 times a second, not faster, because the pump diode cannot charge the fiber fast enough in this time frame to fire it even faster. If you have a stronger pump diode, you can fire the laser even faster, but you don't get more pulse energy, because the pulse energy is determined by the length of the fiber. If we compare this, for example, with these engraving lasers for metals, we have pulse energies of 0.75 to 2 millijoules, but at a repetition frequency of 40 to 100 kilohertz. In the end, it's the same 20 watts average, but there is more pulses for the same time frame. Let's go back in time once again. This is a completely different kind of laser. It uses a gas inside an optical resonator and some high voltage to excite the gas atoms to create coherent light. This is a helium neon laser with around 0.8 of a milliwatt of power. So let's turn it on. And it has this wonderful red glow and excellent beam quality. It has a low divergence and very good frequency stability, and with an almost perfect beam profile, although being quite weak. It was used before diode lasers were a thing, in, let's say, construction lasers for displaying lines on walls and other scientific research purposes, as the frequency of this laser is very stable It was also used for calibrating, but as it doesn't have a lot of power, you can't really process materials with it. So the next bigger thing came out, CO2 lasers. They work on a similar principle. They have an optical resonator cavity filled with gas, in this case CO2, helium and some other gases. The exact mixture is usually a well-kept secret, and if you go to those places where they refill them, they will charge you for that. You will know what I mean if you have to do this once. The gas in the cavity also gets excited by high voltage, usually 20 to 30 kilovolts, and the intensity is controlled by the current. But there's also a different kind of CO2 laser. This is a RF CO2 laser. They come in a metal enclosure instead of glass because they don't use any high voltage. They use an RF transmitter to excite the gas inside the optical cavity. This particular unit has about 10 watts of power, at an input power of about 150 to 200 watts, so they're not really efficient. I've mounted a scan head to the front so I can use it for engraving stuff, but usually that's only the part we're interested in. So let's open the bottom and see what's inside. Underneath the bottom cover we have the control electronics that monitor every aspect of this laser so it doesn't overheat, and provides the PWM control signal for the RF driver. The RF driver is tuned to a particular frequency, which is determined by the laser cavity. The frequency is in the order of 10 to 20 MHz and is affected by gas pressure and cavity length. At this spot where the RF feed-through is connected to, I think I can pull that out, yes, it's just a banana plug. This is also the refill port. The gas inside a CO2 laser has a finite lifespan, and if it's used up, well, you have to refill it. Also, if you run this laser too hot, let's say above 40 degrees Celsius, the gas will deteriorate much faster. These are quite temperature sensitive, so good control electronics are needed, and of course good cooling. The RF generated goes into a metal tube. Unfortunately, I cannot open this metal tube because all the gas will escape and this laser will be useless. It's working perfectly fine right now. So let's close it back up before I do any damage to it. CO2 lasers are available in any size and shape and form, sometimes even to several kilowatts of power. They are used in material processing like cutting steel in conjunction with oxygen. The wavelength a CO2 laser puts out is 10.6 micrometers. It's right inside the thermal range ranging from 8 to 12 micrometers and basically can be seen by a thermal camera. But don't do that, even the weakest CO2 laser will obliterate any thermal camera nearby. It's like staring straight into the sun, even at a reflection, as it outputs a beam of literally heat. In order to cut steel and other metals, we need gases to either push away the material or oxidize it away. For steel, we use oxygen. As the laser heats up the material until it becomes red hot, it starts melting, it starts boiling, and with the presence of oxygen, it starts turning into a gas and evaporates. Lower power CO2 lasers are used for marking organic stuff like leather and wood, most of the time even for cutting wood, like in those hobby CO2 lasers. And these lower powered ones are used for marking on, let's say, plastics, like an expiry timestamp on a product. Fiber lasers, with their precise control of energy and location of the beam through those galvanometers and optics, allow you to create pretty precise and amazing things like this. It's 0.1 millimeters of stainless steel, which I engraved a leather into. But not only that, I made the metal transparent. See? This is achieved by creating a really tightly spaced hole pattern of very small holes that are barely visible even under a microscope, but it makes the material see-through. It's pretty cool. Of course, there's also other applications than just playing around with it. If you want to see more, check out Breaking Tab's channel. He used fiber lasers in several projects. So that's it. That's my overview of my laser collection with a little bit of explanation. Again, not scientifically. If I made any mistakes, let me know in the comments. It's just what I learned over the years and may not be 100% correct at all times. Thanks for watching.